Hello everyone, Aaron here, and we're back in Leetcode. Today we are doing what looks to be another binary search tree problem. This time we are being asked to trim binary search tree. So let's have a quick read of the problem and see what's going to happen. Given the root of a binary search tree and the lowest and highest boundaries as low and high, trim the tree so that all its elements lies in low, high. Now those brackets usually mean it's an open interval, so we will have both. Yes, that looks correct judging by the example. So this is an inclusive value. Trimming the tree should not change this relative structure of the elements that will remain in the tree. Okay, so the tree is going to end up being horribly unbalanced, I imagine, but we'll see what happens. So, return the root of the trimmed binary search tree. Know that the root may change depending on the given bounds. Well, that makes sense. So, for example, if the root is entirely on the left-hand side of the root we are given, then obviously we're not going to keep the original root anyway. We're going to be returning some subtree of the left-hand side entirely. Alrighty, so as last time, we've got a tree node which has been defined for us. It's a value, a left and a right, straightforward enough. It only contains numbers. We've got a low and a high. As before, because it's a recursive data structure, recursive algorithms are almost certainly going to be the way we want to go here. But let's jump on in and start having a go at this. So the base case is if the root is null. Oh my goodness, what is wrong with my typing today? I'm filming this on Good Friday and I've eaten far more chocolate than is good for me already, so typing is a little jittery. If the root is equal to null, return null because we've done everything we can. If the root dot val is equal to the low, well, hang on, no, let's think about this. So if the root val is greater than the high, then we want to return, then basically everything we're looking at right now is just bad. We don't want it. Return trim bst root dot left low high, else if root dot val is less than low. So again, we're entirely on the wrong side. We want to return trim bst root dot left low high. Oops, it's root dot right. Right, so this handles the case where there's absolutely nothing. This second one handles the case where we're entirely to the root value is greater than the high value. Hang on, let me run through this again. I suddenly got myself confused. If the root value, so this thing here, is entirely above the high value. No, hang on. What I'm actually trying to check is if we've fallen entirely outside of the bounds. Yeah, that's correct. So if this is higher than the high value, we must be looking for something entirely on this side. Whereas if it's below the low bound, then we're looking for something entirely on the right-hand side. The last case is where we've got something less useful. What we want to do, we're in the interesting case now. What we want to do is we want to check the value is in the range of things we want to keep. If the value is equal to the low. So this is the leftmost thing that we want to keep. We want then everything on the right is good to keep, and we want to keep the node itself, but we want to return a new tree node, which is made of root.val, nothing on the left, and root.right on the right. If root.val is equal to high, return new tree node root.val, root.left, and null on the right. So now we've got, oops, triple equals because it's TypeScript. So if we're looking at the absolute lowest thing, we want to lop off the left subtree. If we're looking at the absolute highest thing, we want to lop off everything on the right. We don't actually need to descend into the left or the right because they're obviously going to be within the bounds. I guess the one concern is that, hang on, so if we're looking at 1, no, let's do a little example down here. Say our tree looks like, we've got a 3, 2, 5, 1, nothing, 4, 6, and we're looking for everything between 2 and 5, for example. We want to end up with the 3, if I can type, we want to keep the 2 there, we want to keep the 5 there, and that's going to be nothing. Oops. Those are going to be nothings. We want to keep the 4 there, and we want to end up with the null there. So there's this 3 here. So what we really want to do is we want to turn a new tree node, which has the root.val, trim bst on root.left, low, high, trim bst root.right, low, high. We have to continue walking down the tree if we haven't hit any of the edge cases. Because this 3 here, if we didn't have this last line here, what would happen is we would look at it and say it's inbounds, great, we're done. But no, we're not. We've got to check, well, what's happening on the left and right hand side. So we need to go check on the left hand side and trim it to the right shape. We have to go on this side and make sure it's trimmed on the right hand side as well. And then we'll hit one of these cases eventually. That seems pretty promising. I don't love this chain of ifs, but is there an easy way to handle it? Actually, hang on, is this correct? If this is equal to the lower bound, that can still be... that can still expand beyond the high, can't it? That's not what we want. So this needs to be trim bst on the right, because if we hit the root and it happens to be the lower bound, but the right extends way off to be the upper bound, then we're in trouble. So I suspect there's going to be a fair bit of tidying up we can do. Oh gosh, root dot left. No. I wonder, do we even need to special case these two? What happens if we didn't even have that? So let's go back to our tree we had a second ago. We had 3, 2, 5, 1, nothing, 4, 6, and we were going in between 2 and 5. So 3 is obviously not null. 3 is neither above the high bound or below the low bound. So we are going to keep the 3, but then we're going to go in and we're going to go on the trim the BST. We're going to say, well, the root dot left, low and high. So the 2 isn't lower or higher. So that's going to be kept. And I'll come back to the other side in a minute. I haven't lined those up properly. So we go down on this side, we're looking between a 2 and a 5. 1 is lower than low. And root dot right is null. So we're going to end up with a null there. Whereas on the other side, well, we have null anyway, so we're going to return a null. Now back up here, we're looking at the 5. 5 is not above the high value, it is the high value, so we're going to continue into its subtree. 4 is within bounds, so we're going to recurse, but both of its children are null, so it's just going to come back like it is. 6 is beyond the high value. So I think this one here, it's beyond the high value, so we're going to look only at its left. Its left child is null. So we are done. 2, 3, 4, 5. Now, this is probably a bit wasteful. I think having this check in here is going to save us doing a whole lot of searching, because this 5 is the upper bound. We don't actually need to check here and see if there's like a something in between the 5 and the 6. We don't need to check if there's a 5.00001 or something like that, because we're already at the upper bound. So this check will probably just keep things faster. Let's give it a go with both in the test case, shall we? Let's try it without oops, I don't need this floating around. That's going to throw me all sorts of syntax errors. Let's try that. Doom, doom, doom. This looks fairly promising. Let's have a go at adding in the next test case, just to see what we get out. 1, 3. Check if we're still getting correct output the whole way. This looks fairly promising. Let's submit it, see what happens. Feeling pretty good about it. Perfect. We were already fairly quick because we're already beating 80% and we're doing quite good on memory as well. But I'm curious to see what happens if we put back in these checks. So we'll just double check that it still passes the test case. Should do. This doesn't change anything. There's just expected 3 arguments but got 1. Oh. When doing a recursive function call, give all the arguments. It really helps. God, I'm an idiot sometimes. That seems promising. Let's have a looky, see if we've done any better here. In theory, the runtime should have come down a smidge. No idea what will happen to the memory requirements. It went up slightly. That's a bit of a surprise. Perhaps we spent so much longer doing these 2 extra checks that anything we saved in the recursion isn't going to help us. So let's get rid of those. We don't need them. Let's have a short, tidy function. And that looks like everything we've got to deal with today. Thank you very much for watching, and I will see you tomorrow. Bye. Typing is a little jittery.